Hello and welcome again. So I'm sorry for being late in uploading the video, but actually I was having some immense pressure regarding my college schedules. Okay, so let us continue. Now, in the previous discussion, I have completed about the fluid statics. I have told about the fluid, how the governing equation of the fluid statics can be derived. I have also told about the hydrostatic pressure on the flat surface and also on a curved surface in a submerged condition. So, and we also discussed about the concept of center of pressure and its significance. So now let us move on to the very important part, and it is the base of the analytical fluid dynamics. So that is the kinematics of fluids. So what do we mean by kinematics? Okay, kinematics. So it is the science, okay, in which we only talk about the space and time. Okay, space and time. That means if I have a ball, okay, and you have applied some amount of force to the ball, and the ball is following a trajectory. That means there is a cause of the movement of this ball, and that is this force. Okay, so this is the cause of movement of the ball. Okay, movement of the ball. And what is the effect? This motion, okay, sorry, this motion is the effect, right? So the ball moves how much distance in how much time, so that is answered by this kinematics. So we are not interested about this cause of movement, but we are interested on this movement only, so this motion. Okay, that means we will be talking about this x displacement or position, x dot velocity, x double dot, similarly theta, theta dot, theta double dot, these things, right? So we have time and space, so this is covered by the kinematics. Okay, so this is the essentially kinematics is description of motion. Okay, description of motion. Now if we are doing analysis for a solid, then it is pretty much clear, I guess, because in case of solid we have something called cluster of molecules, right? Or you have, that means if this is a solid block, okay, if this is a solid block, this is a solid block, then you know that only after applying a particular amount of force this block will show the plastic deformation, otherwise not. So we can consider this block as the solid, okay, I mean the rigid body. And the rigid, and in a rigid body the particle actually satisfies a property that says that the distance between 2 points or particles, that cannot change. Okay, so this whole block or this cluster of particles, they can be analyzed as a single particle, because they will not change their motion. So they will move in a, if I am considering the translation, so they will move along. Okay, all the particles will move with the same distance. But for a fluid, if I have again the classical example, I have a tank. Okay, I have this tank, Okay, and I have this fluid, right? I have this fluid. So in this case, if I break down this wall, if I break down this wall, then the fluid will start to move. Then the fluid will start to move. Am I correct? So now the problem is that the deformation in the total fluid zone can be different. Okay. So if you are talking about that I have to describe the motion of the fluid, then it becomes a bit ambiguous. Okay. That means how you can describe the motion of a fluid. Okay. I mean you can't take this is as your as a chunk. Let me make it thicker. You can't take this as your chunk of a fluid and take this as a solid, because it can be the case that in this position the fluid is flowing or behaving in a certain way, and in this position the fluid is flowing or behaving like a certain way. Similarly, if you take a chunk from here, then also you cannot say that that for this little fluid chunk, for this little fluid chunk also the fluid will move uniformly all over this chunk. So that we cannot say. So that means we have to go, I mean it is very intuitively I can say that we have to go particle by particle if we are interested for the fluid analysis. Okay, I mean that should be the appropriate thing, because every particle of fluid, because they are not bounded by a very strong intermolecular force, they can move independently, right? Okay, so now having said this, uh, let me tell you that this description of motion can be classified into two parts. Okay, can be classified into two parts. That means how can we describe, okay, this classification on the base on a question, how can we describe the motion? Okay, describe the motion. So one of the description is Lagrangian. Okay, Lagrangian description. So these descriptions are not only true for the fluid, it can be true for any system, fluid, I mean gas, liquid, solid, semi-solid, anything. Okay, because these are just the methods of description of motion. It can be motion of anything. Another is Eulerian. Eulerian description. So let me give you an example. Okay, so let us have a busy road of Kolkata or any other city that comes into your mind. So a busy road. Okay, so this is the road. Okay, and if this is the road, now I have, I should have one traffic police, so that he or she can control the traffic. Okay, so let us just put the traffic police here on this stage type thing. Let us have our, so he is the traffic police, correct? Now his duty is to monitor all the cars if they are violating any rules. Okay, So he can go for two types of views. Okay, so let us say that the first kind of view he or she can have is that, let us say that we have various cars. So this is one car, okay, and maybe this is another car, right? Maybe this is another car, okay. Now, out of all these cars, not three cars actually, there can be many other cars also. Now, among all these cars, he can observe the cars like this. That is, he decides that I will only observe, I will only observe this car. I will only observe this car. So after, so he starts observing at a particular time t equal to 0. So after a time, let us say uh, t equal to tau, okay. After a particular time, t equal to tau, let us say that this car has been moved to this position. Fine. So this is at the time t equal to tau. Sorry. Okay. At the time t equal to tau. So from at the time t equal to 0, the car was here. So that is why I am making it with a dotted sign. Okay. The car was here. Okay. Now the car has moved to this position at a time interval of tau. So he has fixed his observation to this car only. Okay. Okay. So this kind of observation on which you are fixing your observation into a particular, to a particular or a certain particle, so this kind of observation is called a Lagrangian observation or the Lagrangian description of motion. So your observation will be on one particle, one or more than one particle, but generally we cannot observe more than one particle at a time. Okay, so that's why we have to observe only one particle. Okay, I mean more than one independent particle. Now in the second kind of description, he is observing a particular space. He is observing, let us say, a particular space. So he is saying that I will only fix my attention into this space. So he is now pointing a particular or certain car, but he is interested that whatever is entering into this space and whatever is leaving in from this space, and whatever change is happening in this domain. Okay, now he is interested in this domain only, in this space or domain only. Clear? Domain only. Okay, so this kind of observation in which you are only interested in a space or domain, that what is entering into the space and what is coming out from the space and what is changing in the space, so that is called Eulerian description. Okay, so I hope I am clear intuitively. Okay, now let us uh, look into the matter mathematically. Okay, so again let us take an heading of Lagrangian description. Okay, Lagrangian description. So Lagrangian description talks about, okay, focusing your attention on a fluid particle. So this sentence is not 100% correct because I have talked about this fluid. So because I am talking about this fluid mechanics, so that is why I have taken this word fluid. Okay, on a fluid particle. So directly there comes a question, that is one has to start observing at a time at a time t. Okay, and let us say that time is uh, t equal to 0 maybe. Okay, now description of motion means what? We have to uh, we have to come up with an equation of the current position and rather than velocity, okay, and acceleration also, etc., of the current position. So this current one, let us say I am talking about t time t. Okay, so how can we come up with an equation? So my point is that at time t equal to 0, let the particle was here. So this was the point p1, or let us say p0 at time t equal to 0. Now after a particular time interval t, let us say that is time here is t, so this point is p1 now. This point was p0, this point is p1. So this fluid particle has traveled, okay, has traveled through this path, okay, at time t, and it moves from this point to this point. Fine. So now let us say that I have this coordinate system. Okay, let's say that. Okay, so let me do it by another color because I have taken the blue color for the fluid. So this is my origin. Fine, and therefore this is my position vector r naught. So this is the position vector at time at t equal to 0. Okay, and this r naught is a function of, okay, so actually I should have drawn another axis considering the three dimension, okay, three dimensional space. So this r naught is a function of x naught, okay, y naught and z naught. Okay, now this was a parameter of this r naught of my description of motion, that is r naught, because I have started to track the particle from a particular position. So, and that time instant is my time equal to 0. Okay, so what will be now my this position, that is at time t equal to t from origin. So this is r, let us say at t. So that will depend on which thing, because if let us say that I have started to observe from this, okay, from this position, so let us say this is p dash. So then my r naught should have been changed. So had I started to observe from this p dash point, my r naught should have changed, right? And only my known parameter here is, I mean, when I have to describe my motion on this point p1, my known parameters are what? My known parameters are this r naught and this time t. Okay, so that means I have to, I so my equation will be, that is r at time t, okay, this is r at time t, is a function of my initial position at t and t, my initial position and t. Okay, because these two are the only known parameter in my Lagrangian description. There is a certain position vector at time t equal to 0 from where I have started to observe, and there is a certain time interval after which I am interested to measuring the position or anything. So this is the description of Lagrangian motion. Okay, mathematical description of Lagrangian motion. Okay, okay. Now let us go for the second one, that is Eulerian motion. Sorry. So now let us go for the Eulerian description. So again, Eulerian description means I am fixing my attention on a space. So let us consider a pipe actually. Okay, let us consider a pipe. So this is a pipe, fine, and the fluid is moving like this. Now my interest is on a particular space, so let us say this is the space, and I will talk about it later, but actually this is called control volume. Control volume. Okay, so this is nothing but the uh, our domain of observation. Observation. Okay, domain of observation. So from this side some fluid can enter, and from this side some fluid will leave, and maybe somehow there can be some, I mean, if we are maybe interested in measuring some other property like enthalpy, let us say, so that is thermodynamic property. So maybe some of the enthalpy is entering, some enthalpy is leaving, and there is some change in enthalpy also at in this particular time. So we are interested all about these things. Okay, so now that means what will be the particular, uh, let us say that we are interested in measuring velocity. Okay, in measuring velocity. Okay, so what will be the velocity? Okay, what will be the velocity? That will depend on this space, on this space. I mean, if you have chosen your observation domain, let us say here, then the whole analysis may change. That means now uh, your parameter is dependent on the space, and this space is described as also now r. Okay, so this r is nothing but the position vector of the control volume, and also at which time you are measuring, at which time you are measuring, right? So that means this v should be the function of this x, y, z, comma t, or that is nothing but this r comma t. Okay, and here actually this r naught is a function of x, y, z. So here I can write is x naught, y naught, z naught and t. Okay, so the main funda is that you have to be very careful. This x naught, y naught and z naught are the position vector of the particle at time t equal to 0, but this x, y, z are the position vector of the cv at time t equal to uh, actually that will not matter because this position is fixed. Okay, so this is the velocity. Okay, this is the velocity of the uh, whole fluid chunk that is situated in your observational domain. Okay, so this is the uh, maybe a concept of average velocity. Okay, now let me tell you that this control volume may be a square, maybe a rectangle, maybe a circle, maybe any other deformed shape, and also maybe a point. So if you are talking about that I will fix my observation to a point, okay, so then at a through a particular point maybe a particular particle can only pass, but you are fixing your observation to a point. That means that you are interested on a space, and that space is nothing but a point. But you are interested that what is my velocity in that point. So that is an Eulerian description in which your control volume is a point. Okay, so here this velocity is the velocity at or in the control volume. Clear? So these are the two mathematical descriptions, okay, of the motions. Fine. So how can we uh, make the benefits of Eulerian or Lagrangian description, that we will see uh, subsequently. Now I have uttered a term of control volume. Okay, so now let us just tell me you some concepts which are common in thermodynamics and fluid mechanics. So in thermodynamics you have studied about closed system, okay, open system, okay, and isolated system, but I am only talking about this closed system and open system. So this closed system, for this, okay, mass transfer, okay, is not allowed. Okay, for open system mass transfer is allowed. Okay, and for closed system energy transfer is allowed, and for open system energy transfer is definitely allowed because mass is also allowed and some energy can enter with the mass also. Okay, in fluid mechanics I have something called control mass approach and control volume approach. Okay, so this control volume is nothing but equivalent to this open system, and this control mass is nothing but equivalent to this closed system. Okay, so control volume means here can be just an observational domain through which mass can enter, mass can go out, and control mass means a particular amount of chunk of mass, and here the mass cannot change or mass cannot go out or come in. Okay, so these were the concepts of control mass and control volume. And in thermodynamics also we have this concept as closed system and open system. Okay, now let us again move to very important concepts. Okay, okay, so now let me tell you, if you are appearing for any interview, so then they can ask you this very basics, that do you know that what is closed system, do you know that if they give you a particular system, then can you identify that particular system is a closed system or open system. Okay, so this understanding is very important from the point of view of gate, and also from the point of view of your interviews. Okay, so now let us go for the uh, what we call lines of fluid motions, or I should specifically say imaginary lines. Imaginary lines. Okay, imaginary lines of fluid motions. So these are which lines? These are first of all streamlines. Okay, streamlines I have, streak line I have, and which line? Path line I have. These three important lines. So I think uh, we may be familiar to this line, streamline. Okay. So what is the definition of a streamline? It is the line. Okay. The imaginary line on which a tangent on a given point is depicting the direction of velocity at that point at a given instant of time. Okay, so that means here a very important phrase is a given given instant of time. Okay, so if you are talking that yes, these are the streamlines, then the sentence is not uh, actually complete scientifically, because you have to state that these are the streamlines at some at some t equal to tau, or at some t equal to 5 seconds from the observation. Okay, so streamline is can only be defined at a particular point of time. And uh, why that is so? Okay, that is because if I change the time at a particular point, if I change the time, the direction of the velocity can change. That means that the tangent can be changed, and tangent can be changed, that means the curve has to also change now. Okay, so two very important set of words are at a given point of time and at a given point. So this is a concept at a given point. Okay, so it is not talking about a particle. So that means it is talking about a space, or of a domain of observation. So this is nothing but the concept of uh, Eulerian description. So streamline is an Eulerian description. Okay. So this was the definition of streamline. Now, if I have to derive some equation of streamline in terms of the flow parameters, then what can I do? So let us assume that this is a curve, and this curve is depicting the uh, path of the fluid molecules, okay, at a given instant of time. So remember, this is very important, that at a given instant of time, instant of time. So let us say that this is a streamline. That means each of the point on this streamline is having the tangent along the velocity of the fluid at that point. Now let us consider this point. That means if I choose some tangent on this point, I mean I have chosen this point, and now I am drawing this tangent. So that means this direction is depicting the velocity. Okay, fine. Now if I have to, so now just tell me that what do you mean by a tangent? So if I draw any curve like this and I take 2 points here and here, then this line, okay, is a chord, right? So if it is P1 and it is P2, okay, then it is the P1 P2, this straight line is the chord. Now just focus on my words. If I move P2, if I move P2, this point P2 through this arc towards P1, so at the limit P1 P2 tends to 0, and remember P2 is moving towards P1, and at this limit this P1 P2 becomes tangent. Okay, tangent. That means if I move somewhere P2 here, so if I squeeze this down, this picture, then this P1 P2 is very small. So if I name it as ds, then ds this ds vector is along the tangent. Okay, so now from the same definition, from the same definition if I take any ds at this point, so that will be also having the same direction, right? Okay, so that means this ds and dv are in the same direction, and ds is just an elemental vector length, elemental vector that is showing some displacement. Okay, that means this ds is nothing but, if I choose an orthogonal coordinate system, then I can have dx I cap, right, dy j cap, and dz k cap. You can have any other orthogonal coordinate system, actually any other coordinate system. Okay, but in orthogonal coordinate system, here we will analyze only. Okay, so ds and v are in the same direction, so that means the angle between them are 0. So that directly means that v cross ds is nothing but equals to 0, right? So if I have to now derive this cross product, then this I cap, j cap, k cap. So let me say that v equals to u I cap plus v j cap plus w k cap. Fine. Now if it is u, v and w, and I have dx, dy, dz. Okay. Okay. So this is equal to 0. So I cap, so here will be v dz minus w dy plus, okay, minus j cap u dz minus w dx and plus k cap u dy minus v dx equal to 0. And that means that each of the actually this is a vector, null vector. Okay, so all these are 0, that means each of the components must be 0. Okay, because this equals a null vector. So if each of the component is 0, so then this equation gives uh, v by or dy by v equals to dz by w, right? Okay, this gives dx by v equals to dz by w, and this gives what? This gives dx by u equals to dy by v. Okay, and by combining these three, we can have dx by u equals to dy by v equals to dz by w. So this is the streamline equation in in Cartesian coordinate system. Okay, and I am again emphasizing on a point at a given time, right? So this is Cartesian coordinate system. Okay, now if I am given v, okay, v, this velocity as a function of, okay, in polar coordinate system, in coordinate system polar coordinates, or v in spherical. Okay, I mean, this is cylindrical actually, cylindrical, and this is spherical coordinates. So both of these are orthogonal, and in Cartesian coordinate system, we had three directions I, j, k, that is x, y, z, and here we have r, theta, and z, and here we have r, theta, and phi. Okay, so I hope that you know that what these directions of coordinate system means. If you don't know, just search in internet, you can know this. So my point is, you should be able to derive the uh, equation of streamline in any coordinate system, in any, at least in any orthogonal coordinate system. So you will go by only this principle. So this is the basis of the streamline. So if I have this thing, then actually this, so I had xyz in Cartesian coordinate system. Okay, so and these coordinate systems are like, okay, r cap or r, okay, dr. So here I had ds was a function of dx, dy, and dz, right? And so, and dx in cylindrical coordinate system will be dr, rd theta, and dz. Okay, and similarly in spherical system it will be dr. Okay, so this will be some function. So these are just coordinate transformations. Okay, and again, so if I have to derive the streamline equation for the cylindrical coordinate, then it will be, so let us have the, so this is, let us say, unit vectors along the three directions. Then I can have this dr, okay, rd theta, and dz, right? And so now these are the lengths only because vectors are given. Okay, and again I have not du, u, v and w, and that is equal to 0. This gives us the streamline equation in cylindrical coordinate. So my point is, you should be able to derive the streamline equation in any coordinate system. So you have to just have the concept of the basic concept that we have derived this condition by the definition of the streamline, right? Okay. So later we will study something called as stream function after we study the continuity equation. Okay. So now let us move to the next line of visualization, that is streak line, right? That is what streak line. Okay. Sorry. So streak line. Okay. So streak line, this has the definition that uh, imaginary, all these lines are imaginary. Okay, imaginary line made by the locus. Okay, locus of particles, locus of particles which have passed, which have passed um, through a particular point, which has which have passed through but at different uh, previous instance of time. Okay, so that means if I have a point, right, here I have a point P. So let us say that you have started your stopwatch by now, so it has only become t equals to 0, and a particle have passed through this point. Okay, okay. So let us say that after t equal to at t equal to 5 second, that particle that at t equal to 0 was at p point has moved to here. Okay, fine. After 10 and at t equal to 5 second, I have another particle. So let me call these particles as a a1. So another particle. So this particle has passed to the p point at t equal to 5 second. Okay, fine. Again, some after 10 seconds later, this a1, this a1, right, this a1 has moved to here. Okay, and this a2 has moved to here. This is now a2. Okay, so now this is not a2 at t equal to 10 seconds, and at t equal to 10 seconds, like the previous two time instance, another particle a3 has passed through p, Again, you wait for t equal to 15 seconds. Now you see that this A1 has moved to here and this A2 has moved to here and this A3 has moved to here. Okay, so this is at t equal to 15 seconds and a new particle A4 has passed through P. So if you are now at the time instant of t equal to 15 seconds. Now I am writing the timing of each particle when these particles have passed through the point P. So A1 particle, this particle passed through point P at t equal to 0 second. This A2 passed at t equal to 5 second. This A3 passed at t equal to 10 second, and this A4 is passing at t equal to 15 second. Okay, so at t equal to 15 up till t equal to 15, from t equal to 0, from t equal to 0 up till t equal to 15, I have these particles which have passed through the same point at different previous instants of time. This particle passed through P at t equal to 0, this particle at t equals to 5, this at 10, this at 15. So this line is called a streak line. A streak line. Okay, fine. Okay, and so now I am talking about the concept of particles and not about any point or space. So in streamlines we were concerned about a point, whereas in streak lines we are concerned about particles. So uh, this approach is Lagrangian. Okay, now let us straightforward move to path line. Okay, path line. So what is path line? So path line is it is actually very straightforward. It is the locus of the path. Okay, or let us take a good language actually. It is the trajectory. It is the trajectory followed by a particle, a fluid particle actually, a fluid particle up to a given instant of time starting from a particular instant of time. Okay, so I think this is very straightforward that if I have a particle here, now I am starting my stopwatch at t equal to 0, and after t equal to 5 my particle moves to this position. So now this is the P and this was also the P, same particle. So if, and now this is t equal to 5 seconds. So if the particle has moved through this path, let us say, so then this path is called the path line of that particle. Okay, and clearly I am talking about a particle, not a space or a point. So that means this is also a Lagrangian approach. Lagrangian approach, right? Okay. So just focus on a particular thing, that here if I have to, uh, I mean that here the starting point is not fixed. right? So if you are talking about this point, then it is not fixed. If you are talking about this point, then it is not fixed, because the starting time was t equal to 5, the starting time was t equal to 0. So if you have to write the equation of streak line for any particle, then like so then so let me give you a particular example. So let you have velocity component of u as a function of space and time, x and t, and v also something x, y and t. W is also some x, y, t. Okay. So if you have to derive the equation of streak line, so then you will do something like this, that u equals to, right, uh, so dx dt, right. Now this is the u particle. Okay, this is the u particle. Okay, so just now here comes a very important concept. So I have talked about this as my fluid particles. Fluid particles, that means the velocity of these particles is the velocity of the fluid at that particular point. That means now these definitions, u equals to dx dp, is true for a particle, and that will be equal to the velocity of fluid at that point only if this particle is neutral with respect to the fluid. I mean, if you put a stone in a water, a heavy stone, and then if you track the position and velocity of that stone, so will that be equal to the velocity of the fluid? No, because of the uh, stone's own density and other properties, it will influence the fluid and have its own velocity. So by tracking that stone, you cannot say that you have tracked the fluid particles. But if you put something that is very light with respect to the fluid, and that particle will move with the fluid as the fluid moves, in that case only you are able to say that yes, I have tracked the particle velocity and that is equals to the fluid velocity. So this is an imaginary particle that is behaving neutrally with respect to the fluid at any point, and because of that only we can say that the velocity of that particle is equals to the velocity at that point of the fluid particle. So this is the bridge between the Lagrangian and Eulerian concept. Okay, so I am just writing this thing, very important. So velocity of a particle, so obviously neutral with respect to the fluid, is equal to velocity of fluid at that point. Okay, so this is the bridge between bridge between okay, bridge between Eulerian and Lagrangian concept. Fine. So then this thing converges to from u particle to u fluid actually at that point. So that is equals to dxp dt. Okay. Now I have given you some expression for you, and that we will put here. So this becomes ux comma t is equals to dx dt. Okay. Now that means this dt, so I am considering only this. Okay. So maybe, so let us say that after getting the expression of u, you can write this as this, like g of t. Okay. So if now if you are done, so then my question is that what will be the uh, limits for the time. So this will be from 0 to x. Okay. And so if I have to find the find the equation for streak line. Streak line. Okay. Then then I am calculating the locus or the equation of the streak line at a particular instant of time, but I don't know that at what time I have, or that particle have started, because I have many particles in this streak line, but this particle has started at a different time instant, this particle has started at a different time instant, and all this particle has started at a different time instant. So here this t will be variable. Okay. And this will be a fixed time instant. Fixed time instant. But if you are deriving the same, but now your objective is to the derive the, let us say, path line. So then you know that here you are tracking only one particle, and you have started your stopwatch at a particular instant of time, and you know that particular instant of time. So here, sorry, here when you are putting this limit, then the starting time instant will be a constant, and this is a variable, and this is again 0 to x. So now this is my variable. Clear? So this was the major difference between streak line and path line from the mathematical point of view also. Okay. So these were the very important concepts, and now at last let me conclude by mentioning a very interesting and important conclusion that um, okay. So to do this I have to define various flows. Okay. Various flows, or the classification of the flows. So broadly there are very many classifications. I am just doing it like this. So one is based on time dependence. So this is steady, this is unsteady. Okay. Another is based on the position dependence. So this is uniform, and this is ununiform. Okay. Or non uniform. So I am just talking about now this thing, steady and unsteady. Okay. So steady means the fluid properties and velocity acceleration, this will not depend on this will be not the function of time, and unsteady means these things will be the functions of time. Okay. Now, having this concept of steady and unsteady flow, let us look at a very interesting concept. So, let us have a flow domain like this. Okay. So, first of all, let me tell you that streamline means what? Streamline means if I have a streamline at, let us say, at time equals to t1, this instant I have this streamline. That means that if I have a particle here, then this particle is constrained to move in this direction, and this particle in this direction, this particle in this direction, right? So if the streamline does not change with time, then these particles will always be on the same streamline, right? Because the streamline says that which particle will move in which direction, right? So that is governed by the streamline. So if the streamline is not changing with time, then this particle will always move on this streamline only, right? Now let us consider the same case, that is the steady flow. So in steady flow, what does happen? So in steady flow, if I have on any point the velocity direction in this point, so if I take any other time instant t equals to t2, which is greater than t1, then at all these points I will be having the same velocity, the same magnitude and the same direction, right? So if that is the case, then the velocity will be same, and the tangent are remaining same, then the curve will remain same, right? So so that is, in steady flow, streamline is not changing at all. So I can have various streamlines along the flow like this. Now let me consider that I want to find a straight line for which the particles must be passed through this point. So if the flow is steady and a particle has to pass through this point, then what did I tell? Then the particle must follow this streamline. It has no other option remaining. Am I correct? So this particle, all the particles, if any particle is passing through this point, that particle has to follow this streamline, because this particle, any particle passing through this point will be velocity in this direction, and after that this particle will go to this position and this position and this position and so on. That means the streak line and the streamline are same, and if I am tracking a particular particle, so that particle will move through this line only, because it has no other option. So be it any line, all the lines converges to a same line. So for steady flow, stream line equal to streak line equal to path line. This was a very important concept. Another thing, lastly, I want to say, that is, can two streamlines intersect? So let us have this streamline and this streamline intersecting. So that means if I am having at a point, I can have this velocity also and this velocity also. But is that possible? No. At a particular point, at a particular time instant, at a particular point, I cannot have more than one velocity. So that's why, so this was one point, and the second point, two stream lines can't intersect, right? Okay, so with this I am ending this discussion. Always I encourage you to share your thoughts or any suggestions if you have in the comment box. Okay, and keep studying well, keep understanding and feeling the subject. So let us meet on the next discussion. Until then, thank you and take care.